Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today, me and my group members are going to present to you about our constant strain triangle project for our finite element method. Okay, so the objective of this project is to compare the difference and accuracy of the result when using both manual and software analysis. The manual analysis that we'll be using today is Octave, and the software analysis is the Ansys analysis. And the second objective is to determine the optimum number of elements to achieve accurate reading. Okay. Next slide, please. Okay. So in order to use our manual method to search for the variables, this will be the formula that we will be using after derivating it using element method. So that is the displacement function matrix. We will be using this. That is the strain displacement matrix, the stress. The next one, the D for each element, and that is the area for each element, and also the formula of Jacobian. Next slide. Sorry. Okay. Okay, then there is the stiffness matrix, and to find the traction force vector, we'll use that formula. So the use of this formula is to calculate the variables in manual way. We can use it manually, which is by calculating our own self, or we can use it by inserting in programming software such as Octave and MATLAB to ease the calculation if a lot of elements. Since we will be using a lot number of elements, we will be using it in programming software. In this case today is Octave. Okay, next.
Okay, I will explain about the finite element analysis. Before that, my name is Muhammad Nasrullah. I'm using the Ansys software to complete this task, this project. First of all, we must know the model of material. And the first type of element is we choose the static structural. And in the question, we get the properties that the first one is a Poisson ratio that is equal to 0.3, and the Young modulus is equal to 207 gigapascal. And our group that we are given the dimension for R over D is equal to 0.15, and W over D is equal to 1.1. For the thickness, we assume the thickness is 8 millimeter, and all the units in the Ansys that we use is in milliliter. And after that, to set up the modeling, we do a meshing to generate the surface body with 12 elements, and all the mesh are in triangle method. And after that, the point load is 1000 Newton in a positive X direction at right corner of quarter model. For the solution, we only find the X and Y displacement and normal strain and stress at the point of A, B, and C, as we saw in the picture that given. Okay, next. This is the solution that I'm using the Ansys software. At the point A, we can see that at the X displacement, it is a 0. It is because there is a symmetry region in the vertical region, and while at the point C, Y displacement at the point C is 0 because there is a symmetry region at the horizontal plate. And we can see the result for the normal strain and the normal stress for the 3 point that we want to find A, B, and C. Okay, next.
Hello, my name is Nafradas bin Muhammad Zainuddin. I will explain to you about the manual calculation for constant strain triangle. Okay. First, we need to find D. The formula for D is E over 1 minus V2 V square, which means D11 and D22. But the D12 and D21 is different, and D33 also different. So these are the formula, and the formula for Jacobian is J equal to X13, Y13, X23, and Y13. And formula for area is 1/2 delta J. Okay, this the example that we take is element 6. The nodes that we take is 3, and the Q that equal to 0 is 4. So we need to highlight the table that the Q is equal to 0, and we need to find the value for the not highlighted value, which means is 2 times 2. So then we need to find the X13, X23 by using the displacement that given by the Ansys that find in question 2. So we just find the value, then we find the delta J, find the area, and we get the strain stiffness. So between the 12 element, we get the stiffness matrix. So we combine to be a global stiffness matrix. So this is the value. Okay, next. Okay. Then we compare the value of the manual calculation and the octave, but it's slightly different because of, I think, the manual calculation just a little bit different because of mistake of my reading. I don't know. These are the coding for using octave, and this is the value for Q for octave is this. And
Okay, for the analysis for further result improvement, we do this analysis to obtain the optimum number of the element based on the graph that we plot, which is graph Y displacement with number of element. As we can see from the graph, we can observe the optimum number of element that when the slope of the graph start to become a zero slope, as we can see, we can find the optimum number, which is 937 from the graph. Okay, next. Okay, this is the solution for the X and Y displacement, strain in X and Y axis, and the stress of the element. And I find the strain in X and Y axis because I want to find the Poisson ratio to be calculated. Okay, next. Okay, this is the first one that we must find the Poisson ratio. Before that, we must use this equation that Poisson ratio is equal to negative normal strain in y-axis over normal strain in x-axis. And we use the average for the normal strain, and we substitute it into the equation, and we will get the answer 0.296 for the Poisson ratio. And the Poisson ratio that given in the equation is 0.3. And after that, we calculate the percentage error, and we get only the small in percent, which is 1.33%. And after that, we can find the stress concentration factor, KT, using the formula of KT is equal to stress maximum over stress not, and we can find from the Ansys that stress maximum is equal to 3.4084 megapascal, and the formula for the sigma naught is equal to F over D times T. D is we assume in this equation, and the T is 8 millimeter that we assume to. And we can get the value of concentration factor, stress concentration factor, 1.7996. And from the table, our KT is equal to 2.0. And then we calculate the percentage error, and we get 10.02%. Okay, next.
Okay, so now I'll be explaining to you the comparison between using 12 elements and the optimum number of elements, which is 937. I'm going to show you the difference between using the number of elements. First, as you can see at the table where it shows X directional deformation and also Y directional deformation. When using the 12 elements for X directional deformation, you can see at point A, point B, point C, the value of when you use 12 elements is less than when you use 937 elements. This also the same way when for the Y directional deformation. So it can be said that when using for the displacement, when you use more number of elements, yeah, it is more accurate when the displacement is in a larger value, and when you use the more number of elements, the result that you will get is more accurate. Okay, so next slide, please. And then the next slide. Okay. So the next example I will use is the stress. So as you can see, the one for the 12 elements for point A is 1.7913, while the one for the 937 elements is 3.4084. And for the point B, the 12 elements one is 1.7289 MPa, and the one using the optimum number is 0.55316. And for point C, the one using 12 elements is 1.6469, and the one using optimum number of elements is 1.6448. So this proves that using the different number of elements it will shows different result, whether it is accurate or not in our study. Next one, please. Okay. So then we calculate the Poisson ratio. So the theoretical value for the Poisson ratio which is given to us is 0.3, but when we calculate using the optimum number of elements, we got 0.296, which is not a big difference with the percentage error of only 1.33. So the value is quite similar, so that means there is very little, there is minimal error in our calculation. And for the stress concentration factor, and the theoretical value given is 2.0, and the one that we calculated with the optimum number is 1.7996, which is also not far off with percentage error of 10.02. So so for any percentage error, it's probably due to any manual errors during the calculation in the software, but it is not that much. So that means it is actually quite similar. Okay. That's all.
Based on the discussion that we get is based on the table for displacement in X and Y direction, it can be observed that the deformation when using optimal number of elements is larger compared to using 12 elements. Using the optimum number of elements is more accurate, as the more the number of elements used, the accurate the result will be. The result for the stress concentration factor has a percentage of error of 10.03%, while the Poisson ratio is 1.33%, which is only minimal. However, results from using manual and software method are different, which are probably due to manual error made by human. The conclusion is, in conclusion, both methods can be used for finite element analysis. However, in order to achieve the most accurate result in a problem using a lot of elements, it is more preferable to use any software as it is more efficient and accurate than human. Thank you.